Hello and welcome back everyone. In today's video, we will take a first look at the ideal buck converter transfer functions in continuous conduction mode, the small signal model that forms the foundation of every compensator design. We will explore the three fundamental transfer functions: control to output transfer function, line to output transfer function, and output impedance. We will interpret their body diagrams using actual hardware parameters. Here is the schematic of a voltage mode controlled synchronous buck converter. You can see the full power stage on the left. The output voltage is sensed through the feedback divider and fed into the summing node where it is compared to the reference. The difference between the reference and the measured output generates the error signal, which is then processed by the compensator. The compensator output is the control signal that drives the PWM module. The PWM drives the gate drivers, and the gate drivers switch the MOSFETs that regulate the inductor current and output voltage. The output is then measured again, and this closes the control loop. Now, the important question: why do we need a small signal model of the buck converter? To design the compensator, we need a mathematical model of how the converter behaves around its operating point. In continuous conduction mode, the buck converter can be represented by three small signal transfer functions, which you see here. GVD of S is the control to output transfer function, GVG of S is line to output transfer function, and Zout is the output impedance. These transfer functions describe how the converter responds to changes in duty cycle, input voltage, and load current. On the next slide, we will look at the analytical expressions for all three. Let's start with the three fundamental transfer functions of the buck converter in continuous conduction mode. The first is control to output transfer function, or GVD of S. This transfer function tells us how the output voltage responds to small changes in duty cycle. It is the core plant model used for compensator design, bandwidth selection, and stability analysis. Next is line to output transfer function, or GVG of S. This describes how input voltage disturbances propagate to the output. It is critical for understanding line regulation and for designing feed-forward techniques if needed. At the end, here is also the output impedance, or Z out of S. This transfer function shows how the output voltage reacts to changes in load current. It is directly tied to load transient performance and output capacitance selection. Although the numerators are different, all three transfer functions have exactly the same LC denominator. This is because they all originate from the same averaged state space model of the buck converter. The natural frequency omega 0, quality factor Q, and the LC double pole appear in all of them. These transfer functions form the mathematical foundation for everything that follows: loop gain construction, type 3 compensator design, digital implementation on the C2000, stability and transient response analysis. On the next slide, we will look at the frequency response for the control to output transfer function, or GVD of S. Now that we have seen the analytical form of the control to output transfer function, GVD of S, let's look at what it actually does in the frequency domain. Here is the same transfer function from the previous slide, but now expressed through its body diagram using the real hardware parameters of our converter. You can immediately see the three most important characteristics: low frequency gain, a strong LC resonance peak determined by the quality factor Q, a minus 40 dB per decade roll off beyond the resonant frequency, and phase drop approaching minus 180 degrees around resonance. These characteristics are exactly what make voltage mode control challenging, especially when attempting high bandwidth with type 3 compensators. These are the electrical parameters used for this plot. Inductance is 4.8 microhenries, capacitance is 396 microfarads, load resistance is 1.58 ohms, input voltage is 9 volt, and output voltage is 2 volts. From these values, we compute the DC gain, which is approximately 19.08 decibels. Then resonant peak is around 42.3 decibels, and the natural frequency is around 23 kiloradians per second. This transfer function, GVD of S, is the foundation of the entire compensator design. Every pole, every zero, and the final loop bandwidth of the Type 3 compensator will be chosen relative to this blend. On the next slide, we will take a look at the frequency response of the line to output transfer function, or GVG of S. Here is the line to output transfer function GVG of S along with its parameters and Bode diagram. Just like before, the denominator is the same second order LC system, but now the low frequency gain is simply the duty cycle D. This means that input voltage disturbances are transferred to the output proportionally to the operating duty cycle. Here are the exact parameter values used for this plot, the same as in the previous slide. At a low frequency, the gain is 0.22 or minus 13.06 decibels. This tells us how much of the input voltage ripple appears at the output in steady state. Next, we again see the LC resonant peak. Its magnitude is determined by the quality factor Q, which is roughly 42.3 decibels for this ideal converter. And the resonant frequency remains the same, around 23 kiloradians per second. Above resonance, the slope drops at minus 40 dB per decade because this is still a second order system. This transfer function is important because it describes how input voltage disturbances propagate to the output. If your upstream supply introduces ripple, switching noise, or load interaction disturbances, this diagram tells us exactly how much of that noise will reach the output. Later, when we design the compensator, and especially if we use feed-forward, this transfer function becomes key for improving line regulation performance. Before we finish, if you want to control your buck converter in voltage mode control and you don't want to start completely from scratch, you can check out my free buck converter toolkit on HK Academy. It contains LT-SPICE models, Octave scripts, and C2000 examples that will help you get a working design very quickly. The link is in the description. In the next video, we will continue this series and see how the series inductor resistance, RL, changes the transfer function and how it modifies the Bode diagram of the buck converter. Thanks for watching and see you in the next video.